Welcome to our comprehensive guide on data preprocessing techniques. In today's data-driven world, preparing your data correctly is the foundation for any successful analysis or machine learning project. Data preprocessing involves a series of steps that help transform raw data into a clean and usable format. This process not only improves the quality of your data, but also ensures that your models perform at their best. Throughout this video, we'll explore the essential techniques, practical tips, and common challenges you might face. Let's start by understanding why preprocessing is so crucial before diving into the specific methods. Data rarely comes in a perfect state. It often contains errors, inconsistencies, or missing values that can negatively impact your analysis. Preprocessing helps address these issues by cleaning and transforming the data, making it more reliable and suitable for further processing. Without proper preprocessing, even the most advanced algorithms can produce misleading results. By investing time in this step, you set a strong foundation for accurate insights and robust model. Next, let's look at the first step, data cleaning. Data cleaning is the process of detecting and correcting errors or inconsistencies in your dataset. This includes handling missing values, removing duplicates, and correcting incorrect entries. Clean data ensures that your analysis is based on accurate information, reducing the risk of drawing false conclusions. It's important to approach data cleaning systematically, checking for common issues and applying the right fixes. In the next scenes, we'll break down the most common data cleaning techniques and how to apply them effectively. Missing values are a frequent challenge in real-world datasets. There are several ways to handle them depending on the context and the amount of missing data. You can remove rows or columns with missing values, impute them using statistical methods, or use algorithms that can handle missing data directly. The choice depends on how much data is missing and how critical that information is. Let's explore each approach and discuss when it's best to use them. Duplicate records can skew your analysis and lead to inaccurate results. Identifying and removing duplicates is a key step in data cleaning. This process involves checking for repeated rows or entries and deciding which ones to keep. Most data analysis tools offer functions to quickly find and eliminate duplicates, ensuring your dataset remains unique and reliable. After handling duplicates, your data will be more consistent and trustworthy for further processing. Consistent data, such as varying formats or typos, can cause confusion and errors in your analysis. Standardizing formats, correcting spelling mistakes, and ensuring uniformity across your dataset are essential steps. For example, dates should follow a consistent format, and categorical values should be standardized. This attention to detail helps prevent issues during analysis and modeling. Next, we'll discuss how to detect and address outliers in your data. Outliers are data points that differ significantly from others in your dataset. They can result from errors or represent rare but important events. Detecting outliers involves using statistical methods or visualization tools to identify unusual values. Once found, you need to decide whether to remove, correct, or keep them depending on their impact. Handling outliers appropriately ensures your analysis remains accurate and meaningful. After cleaning, transforming your data is the next crucial step. Data transformation involves converting data into a suitable format for analysis. This can include scaling numerical values, encoding categorical variables, or normalizing data ranges. Proper transformation ensures that your data meets the requirements of your chosen algorithms and improves model performance. Let's dive into the most common transformation techniques. Scaling is essential when your dataset contains features with different units or ranges. Common scaling methods include min-max scaling and standardization. Min-max scaling transforms values to a fixed range, usually 0 to 1, while standardization centers the data around 0 with a standard deviation of 1. Choosing the right scaling method depends on your data and the algorithms you plan to use. Proper scaling helps models converge faster and perform better. Normalization is another technique to adjust the scale of your data. Unlike standardization, normalization typically transforms data to a range between 0 and 1. This is especially useful when you want to compare features with different units or magnitudes. Normalized data ensures that no single feature dominates the analysis due to its scale. Let's see how normalization differs from standardization and when to use each method. Many datasets include categorical variables such as labels or categories. Machine learning algorithms require numerical input, so encoding these variables is necessary. Common encoding methods include one-hot encoding and label encoding. One-hot encoding creates binary columns for each category, while label encoding assigns a unique number to each category. Choosing the right method depends on the nature of your data and the algorithm you're using. Binning or discretization involves converting continuous variables into discrete bins or intervals. This technique can help reduce the impact of minor observation errors and make patterns more apparent. For example, age can be binned into groups like child, adult, and senior. Binning is useful for certain algorithms and can simplify the interpretation of results. Let's explore how to apply binning effectively. Feature engineering is the process of creating new features or modifying existing ones to improve model performance. This can involve combining variables, extracting information, or transforming data in creative ways. Effective feature engineering can reveal hidden patterns and boost the predictive power of your models. In the next scenes, we'll discuss common feature engineering techniques and their benefits. Sometimes, combining existing variables or deriving new ones can provide valuable insights. For example, you might create a total spend feature by adding up several spending categories. New features can capture relationships that aren't immediately obvious in the raw data. The key is to experiment and evaluate which features improve your model's performance. Let's look at some practical examples of feature creation. Not all features are equally important. Feature selection involves identifying and keeping only the most relevant variables for your analysis. This can help reduce overfitting, speed up training, and improve model interpretability. Common techniques include correlation analysis, recursive feature elimination, and using model-based importance scores. Selecting the right features is a critical step in building effective model. Your dataset has many features, it can become difficult to analyze and model effectively. Dimensionality reduction techniques such as principal component analysis (PCA) help reduce the number of variables while retaining important information. This simplifies your data, speeds up computation, and can even improve model performance. Let's discuss how dimensionality reduction works and when to use it. Data integration involves combining data from multiple sources into a single, unified dataset. This is common when working with data from different departments or systems. Integration can reveal new insights and provide a more complete picture for analysis. However, it also introduces challenges, such as resolving conflicts and ensuring consistency. Careful planning and validation are essential for successful data integration. Data reduction aims to decrease the volume of data while preserving its integrity. Techniques include aggregation, sampling, and dimensionality reduction. Aggregation combines data points, sampling selects a representative subset, and dimensionality reduction simplifies features. These methods help manage large datasets, reduce storage costs, and speed up analysis. Choosing the right reduction technique depends on your specific needs and goal. Discretization is the process of converting continuous data into discrete categories or intervals. This can make data easier to interpret and is useful for certain algorithms that require categorical input. Methods include equal width binning, equal frequency binning, and clustering-based approaches. Discretization can also help reduce the impact of noise and outliers in your data. Aggregation involves summarizing data by combining multiple values into a single value. For example, you might calculate the average sales per month or the total number of transactions. Aggregation helps simplify large datasets and can reveal important trends. It's a common technique in both data preprocessing and analysis, especially when dealing with time series or group data. Sampling involves selecting a subset of data from a larger dataset. This is useful when working with very large datasets that are difficult to process in full. Sampling methods include random sampling, stratified sampling, and systematic sampling. The goal is to create a representative sample that maintains the characteristics of the original data. Proper sampling ensures your analysis remains accurate and efficient. Partitioning involves dividing your dataset into separate parts, such as training and testing sets. This is essential for evaluating the performance of machine learning models. Proper partitioning ensures that your models are tested on unseen data, providing a realistic measure of their accuracy. Common splits include 70-30 or 80-20 for training and testing. Partitioning is a key step in any data science workflow. Shuffling your data is important to prevent any order-based biases during training. This is especially relevant for time series or sequential data. Randomly rearranging the data ensures that your models learn general patterns rather than memorizing the order. Most data processing libraries offer simple functions to shuffle datasets efficiently. Shuffling is a small but crucial step in preprocessing. Classification tasks. Imbalanced datasets can lead to biased models. Data balancing techniques such as oversampling the minority class or undersampling the majority class help address this issue. Balancing ensures that your model pays equal attention to all classes, improving its ability to generalize. Let's discuss the most common balancing methods and when to use them. Noise in data refers to random errors or irrelevant information that can obscure true patterns. Noise reduction techniques such as smoothing, filtering, or aggregation help clean up your data. Reducing noise improves the signal-to-noise ratio, making it easier for models to learn meaningful relationships. Let's explore practical ways to minimize noise in your datasets. Smoothing is a technique used to reduce noise and make patterns in data more visible. Methods include moving averages, exponential smoothing, and kernel smoothing. Smoothing is especially useful for time series data where it can help identify trends and cycles. By applying smoothing, you can create clearer visualizations and improve model accuracy. Filtering involves removing unwanted or irrelevant data points from your dataset. This can include outliers, errors, or data outside a specific range. Filtering helps focus your analysis on the most relevant information, improving the quality of your results. Various filtering techniques are available depending on the type of data and the goals of your analysis. Log and power transformations are used to stabilize variance and make data more normal. These transformations are especially helpful when dealing with skewed data or variables with exponential growth. Applying log or power transformations can improve the performance of many statistical models and make patterns more apparent. Let's see how and when to use these transformations. Balanced data can cause models to favor the majority class, leading to poor performance on minority classes. Techniques like synthetic minority oversampling technique, SMOT, and random undersampling help create balanced datasets. Balancing your data ensures fairer and more accurate models, especially in classification tasks. Let's discuss how to implement these techniques effectively. Categorical variables can be ordinal or nominal. Ordinal variables have a natural order while nominal variables do not. Encoding these variables correctly is crucial for model performance. Ordinal encoding assigns ordered values while nominal variables are often one-hot encoded. Understanding the difference helps you choose the right encoding method for your data. Hex data requires special preprocessing steps such as tokenization, removing stop words, and stemming or lemmatization. These techniques help convert raw text into a structured format suitable for analysis. Proper text preprocessing improves the accuracy of natural language processing models and makes it easier to extract meaningful insights from unstructured data. Image data also requires preprocessing such as resizing, normalization, and augmentation. These steps ensure that images are consistent in size and scale and help improve the performance of computer vision models. Augmentation techniques like rotation or flipping can increase the diversity of your dataset and make models more robust. Time series data has unique characteristics such as temporal order and seasonality. Preprocessing steps include handling missing timestamps, resampling, and detrending. These techniques help prepare time series data for analysis and modeling, ensuring that temporal patterns are preserved and accurately represented. Automating data preprocessing can save time and reduce errors, especially when working with large or frequently updated datasets. Tools and libraries like scikit-learn, pandas, and TensorFlow offer functions to automate common preprocessing tasks. Automation ensures consistency and allows you to focus on higher-level analysis and modeling. Validation is the process of checking your data for errors, inconsistencies, or outliers after preprocessing. This step ensures that your data is ready for analysis and modeling. Validation techniques include summary statistics, visualizations, and automated checks. Proper validation helps catch issues early and improves the reliability of your results. Pipelines allow you to chain multiple preprocessing steps together, ensuring a consistent and repeatable workflow. Tools like scikit-learn pipeline make it easy to build and manage preprocessing sequences. Pipelines help prevent data leakage and make your code more organized and maintainable. Let's see how to create and use preprocessing pipelines effectively. Preprocessing isn't always straightforward. Common challenges include dealing with large datasets, handling complex data types, and ensuring data privacy. Each challenge requires careful planning and the right tools. By anticipating these issues, you can develop strategies to overcome them and keep your projects on track. Following best practices can make your preprocessing more effective and efficient. Document your steps, use version control, and validate your results regularly. Stay updated with the latest tools and techniques, and always tailor your approach to the specific needs of your data and project. Best practices help ensure high-quality, reproducible results. Machine learning models are sensitive to the quality and format of input data. Proper preprocessing ensures that your data meets the requirements of different algorithms and improves model accuracy. This includes scaling, encoding, and handling missing values. Tailoring your preprocessing to the needs of your model is key to achieving the best results. Deep learning models often require more extensive preprocessing, such as normalization, augmentation, and data balancing. These steps help models learn more effectively and generalize better to new data. Deep learning frameworks provide tools to automate and streamline preprocessing, making it easier to handle large and complex datasets. Big data presents unique preprocessing challenges due to its volume, variety, and velocity. Distributed processing tools like Hadoop and Spark can help manage and preprocess large datasets efficiently. Techniques such as sampling, aggregation, and parallel processing are essential for handling big data. Let's explore strategies for preprocessing at scale. Real-time data requires fast and efficient preprocessing to keep up with incoming streams. Techniques include windowing, filtering, and incremental updates. Real-time preprocessing ensures that your models and dashboards reflect the latest information, enabling timely decision-making. Specialized tools and frameworks are available to support real-time data workflows. Ethical considerations are increasingly important in data preprocessing. This includes ensuring data privacy, avoiding bias, and maintaining transparency. Ethical preprocessing practices help build trust and ensure that your analysis is fair and responsible. Always consider the ethical implications of your preprocessing choices. We've covered a wide range of data preprocessing techniques, from cleaning and transformation to feature engineering and validation. Each step plays a vital role in preparing your data for analysis and modeling. By mastering these techniques, you can ensure that your data is accurate, reliable, and ready for any analytical challenge. Congratulations on completing this journey through data preprocessing techniques. Remember, high-quality data is the backbone of successful analytics and machine learning projects. Continue practicing these techniques, stay curious, and keep exploring new tools and methods. With a solid foundation in data preprocessing, you're well equipped to tackle any data challenge that comes your way.